My name is John Liddell. It's my pleasure to introduce you to tonight's activities and introduce our speaker. Firstly, however, I would like to acknowledge that we are meeting on the land of the Kulin Nations and pay our respects to their elders, past and present. Welcome again to our monthly Beyond Zero Emissions discussion group. We'd like to thank the University of Melbourne Energy Institute, our Zero Carbon Australia project partners, for this great venue. And for the people amongst us here who have not been to one of our discussion groups before, BZE is a climate solutions think tank and research organisation. Our goal is to transform Australia from a 19th century fossil fuel-based economy to a 21st century renewable powered clean tech economy. And we're still working on it. Our projects include the Zero Carbon Australia Research, Repower Australia talks, media work, educational programs, and much more. We're always looking for more volunteers to come and talk to us. So if you want to volunteer, come and talk to us after the meeting if you want to get involved. This discussion group is a forum for climate change solutions with presentations by experts in their field, and is held every first Monday, on the very first Monday of every month. Tonight couldn't be a more relevant subject given what we've heard from Tesla and their announcement of the Powerwall very recently. Our discussion topic is electric vehicles and energy storage. What do they mean for the grid? Dr. Julian de Hoog is a research staff member at IBM Research Australia, working on a variety of projects in the energy space across renewables, storage, and electrified transport. Julian was formerly a research fellow in the Department of Mechanical Engineering at the University of Melbourne, and now continues to be involved with the university as an Honorary Research Fellow in graduate student supervision and joint research. His research expertise covers electric vehicles, smart charging, management of distribution networks, and smart grid applications. Ladies and gentlemen, welcome Julian. Thank you.
So, thank you very much for the nice introduction. I've been involved in small ways with Beyond Zero Emissions over the years, but I've always thought what you guys do is absolutely brilliant, and I fully support it. So when I got invited to speak, I thought it was an honor, and I'm really happy to be here, and I get to speak about one of my favorite topics, which is fantastic. So last month, my first slide is already a stolen slide. Last month, Peter gave a brilliant talk about the state of energy supply and networks and some of the products coming onto the market and vehicles and motorcycles and all kinds of things. So I'm not going to go into all that, into what sort of vehicles are on the market, because he did an amazing job of describing all of that last month. But I just wanted to ask Peter, you need a new car. Did you have a chance since then to get your Tesla, or are you still shopping around? So I don't know if you went to the EV Expo last weekend, but there's some amazing cars on display there. So just to add to some things he said last month, I guess I've been following electric vehicle news pretty closely for 3-4 years. And when I first joined this project at the University of Melbourne in February 2012, all the news was EVs are going to change the world, it's going to be amazing, sales are going to skyrocket. And I thought, yes, awesome project. And then 2 months went by and suddenly all the news was EVs are a sham and it's a myth and it's not going to happen and battery storage is never going to, fundamental limits and so on. I thought, oh no. And then 2 months went by and all the headlines were really good again. So it's been a roller coaster over the last few years. And we've had meetings at the university where senior academics were quite skeptical about EVs. Why research? It's just a fad. But if you look at what's been happening, it started with only Tesla in 2008, developing pure EVs. In 2011, there were sort of 4, pure EVs on the market. 2014, we're seeing at least 10 manufacturers, and now I'd say every single major manufacturer is producing electric vehicles. So certainly all the big players are betting on this as something that could become quite big, and at the very least we need to prepare for it, and also prepare in terms of how we manage our electrical networks. So I'm going to talk a 2-part talk, first mainly about electric vehicles, because it's what I've spent more time on. We're going to talk about what sort of impacts they will have on the grid, what we can do about it in terms of shifting that load, and there are both centralized and distributed ways to do that. There are a few quite sort of interesting quirks to distribution networks when you get to modeling at that very last mile sort of level of individual houses. Some unexpected things start to happen, so I'm going to explain some of those. And then, depending on how long I talk and how much time's left, I'd like to also talk about some energy storage work we've done in terms of analyzing how to best charge and discharge energy storage and what kind of value you can get out of it. So, for 3 years, I was here at the University of Melbourne working on this project with a very dedicated group of researchers. Valentin is here near the back today, so all the hard questions I'll push his way. The original main partner was Better Place, and for those who don't remember Better Place, they were a very early player in electric vehicle space. They wanted to bring in charge swap stations that you could own vehicles, drive into a station, pop the empty battery out, and pop a full one in. And I thought it was actually a great business plan because it meant that people didn't have to pay for the battery, they could just lease it, and you could recharge really quickly, faster than you can fill a petrol tank. You didn't need to go home and plug in. So why they ended up actually failing, they went bankrupt. There must be a wide number of reasons for that, and I don't know all of them, but I would guess that they maybe were a bit too early, ran into regulatory hurdles and people who just weren't ready for it. Maybe expanded too quickly, but for whatever reasons it didn't work out. But anyway, at least they funded our project, which was great. So they were an early partner, then we also had Synergy as a partner. We worked together with SP Osland and United on modeling on getting network models and understanding the actual grid better. We worked with DS and with Victoria Department of Transport as part of our involvement in the Victoria Electric Vehicle Trial. So the original motivation for this 3-year research project was kind of summed up in this fake press release that was written at the very start of the project, and that was supposed to be sort of a guidance for what the project was supposed to achieve. So you don't have to read it all, but the highlighted sections indicate the key points. Develop an optimal charging policy informed by the changing electricity spot price, the state of charge in every battery, while also taking into account the present and anticipated constraints in the distribution network over your charging horizon. And doing all of that in such a way that you could achieve maximal uptake of electric vehicles with minimal capacity upgrade requirements in the distribution network. So in other words, figuring out what kind of impacts electric vehicles have when they start to charge, and then finding ways to add as many as possible to our networks in such a way that we don't have to invest in huge infrastructure upgrades. So the first step in understanding that problem and solving it was to develop a good simulation environment in which we could play around and get to know these impacts better. So I'll just take 5 slides to explain how we simulated these things. For our electrical distribution networks, so this is the grid at sort of the neighborhood level, we actually got models of some real neighborhoods, both here in Melbourne and in Queensland and Townsville. And we worked together with the distributors to understand exactly what the distances were, what types of cables they were, how big the transformer was, all those sorts of things. We got real demand data for these networks, so we could know exactly when the peaks were, what time you get peak demand, how this was allocated to different phases in the network. We also used real Victoria Department of Transport travel data to figure out how people typically travel. So to understand the impact of EVs on the network, you need to know how far people have traveled so that you can figure out how long they need to recharge for, and also when they're home. So every couple of years, the Victoria Department of Transport does a survey where all the participants answer questions for 24 hours. I got in my car at this point, I got home at this point, I've driven this far, and so on. So this is a sort of tens of thousands of records that we had, and we could even specifically choose the ones specific to the networks we were modeling, because people in the CBD will have very different vehicle travel patterns than people living in Alpham or further out. And finally, we took all those things together and we stuck them into a simulation package. We used MATLAB SimPower Systems. We could put in how much the houses use, how much the vehicles use, run the simulations, and that told us exactly what the typical voltages and currents throughout the networks would be, not just at the transformer level, but even at each individual house. So what would this mean for the network at each individual house? And then just to make sure that we were doing a good job of this and we weren't just making this up in simulation, we underwent a validation exercise where we got, again, real data from the network operators where they stuck loggers on their lines, took their data and compared it to our own data over a 24-hour period, checked that the voltages we were sort of simulating were close to the voltages that they actually measured in the network. And typically the voltages would be within 1.5 volts on average, and currents within 6 amps. So it was no model is perfect, and this one wasn't perfect, but it was really good. So we were fairly confident that everything we got out of this would be reasonably true to reality. So some of the early results, the first things that came out, what actually happens when you plug in an electric vehicle? What does it do? Well, the first thing that probably everyone thinks of is peak demand, and how much does it add to peak demand? And so I'm going to just show some results for a specific neighborhood with real demand data. In this case, we're pretending that every second house has an electric vehicle. Now that's not going to happen for a long time, but it was just a really good way to visually show exactly what the impacts are. So if every second person in this neighborhood had an electric vehicle, then this is what your peak would look like. So the light blue is your typical household demand profile. We're going from 8 in the morning until 8 in the next morning, and you can see there's a little bit of a peak at the start of the day when people are waking up and turning on coffee machines, whatever. Then there's this big peak demand, and sort of at the time when people come home from work and turn on their TVs and their lights and heating and whatever else, cooling. And then it drops off overnight, and then you have another small peak. And if you assume that people travel with electric vehicles in the same way that they all traveled according to this travel data that we got, arrive home at the same time, all very reasonable assumptions, then this is the dark blue is the sort of demand you would get on the grid from electric vehicles. So as you'd expect, you have exactly high amount of demand from electric vehicles right at the same time you have a high demand of household demand anyway. And that's really bad for the networks because it puts a lot of load on the transformers and the lines. They have nominal limits. If you exceed those a little bit, that's okay, but if you exceed them too much, then it leads to premature aging. Too much current going through them means that they need to replace them regularly. It gets very expensive. So that's the obvious one. Perhaps less obvious is voltage being a real issue. And actually, when we ran these simulations, we discovered that this becomes a problem before peak demand becomes a problem. So each house in your neighborhood will have a slightly different voltage. The voltage is supplied at the transformer, and then as you travel down the street, down the line, voltage will decrease slightly from house to house, usually only just a little bit. But if you measure voltage at your house and you go a few houses up the street and you measure voltage there, it'll be a little bit different. And the reason is that the lines themselves have an impedance. So as current travels through the lines, that voltage will drop slightly from one house to the next. So that's been true for electrical networks forever, but if now you add electric vehicles, which are big loads, and especially if you add several at the same time, then you're drawing all that additional current, and that means that the voltage drops by quite a bit more going down that line. And so the voltage at each house has to be kept within specific limits, and everything that you use is designed to operate within those limits. And if the voltage drops below that minimum limit, again, it's not a catastrophic thing. Your house won't blow up, and the grid won't go up in flames, but things that you're using in your home will possibly age faster. So if you have a low voltage and your washing machine is requiring a certain amount of power, as the voltage drops, it needs to draw more current to enable that sort of power. More current means it heats up and it ages faster. And this is true not just at the houses that have the electric vehicles, but it could be their neighbors. So you could plug in your EV, and 3 houses down, your neighbor will have to replace his washing machine in 5 years instead of in 10 years. So that's not that extreme, but this is sort of the impacts you have. And this is true, of course, for all big loads, for air conditioning and for heating and so on. So this is not some new phenomenon that's electric vehicles, that's unique to electric vehicles, but because they are such big loads, and because they would run for such a long time if they were charging, and because they typically all charge at the same time, it's a bit more of a problem. And then a third important thing to consider as well, which is sometimes neglected a little bit, is balance between the phases. So most networks are supplied 3-phase power, and most houses connect to one of those phases. So in your neighborhood, you'll see 4 lines going down your street, and those are phases A, B, C, and the neutral. And your house will connect to one of those phases and to the neutral. And ideally, in a neighborhood, you want roughly the same number of houses on each of those phases so that they balance nicely. If they balance nicely, that means you don't have any current going through the neutral. But if they're unbalanced, if for whatever reason when they connected the houses they put too many on phase A or on phase B, or took a bunch off phase C, then these phases become quite unbalanced, and so you end up having quite a lot more current through the neutral, which also in turn makes the voltage drop a bit more. And if they're unbalanced already, and then you add lots more load, then like if you add a lot of electric vehicles, then this really exacerbates this problem of voltage, low voltage. So another thing that was really interesting when we sort of ran these early simulations and sort of checked out what happened was that the place in the network that you live at is really, really important in terms of you get very unique effects. So this is a neighborhood in northern Melbourne, and the squares, circles, and triangles are true to the real network in terms of phase connection. And if you were to count them, you would discover that in this network you have 50 houses on phase A, 43 on phase B, and 21 on phase C. So it's quite unbalanced. You have more than twice as many on phase A as compared to phase C. This is just, I think network operators for the most part don't know which houses are on which phases. I think that's changing because they're starting to discover how important it is. But certainly a couple of years ago when we were talking to network operators, one way to discover which houses were on which phases was if there would be a fault on one phase, and then you could check, okay, these 10 houses all had their lights go out, okay, they must all be on phase C, so it's not very advanced. I think with smart metering, the methods are definitely there to start to automatically figure out which houses on which phase, but until now this has just been a case of sticking your house in, connect it, that guy's on B, that guy's on C, okay, I'll stick him on A. Or sometimes I've even heard that when they connect a house, the line that is closest to the street is overloaded just because the guy connecting it just can't be bothered reaching that extra further. So, and I've actually heard another story in the UK that installers there will connect to the phase that is equivalent to the football team they support. So if you're an Arsenal supporter, you're always putting the houses on phase A. If you like Chelsea, you're going to put them on phase C. So I'm not sure if it's true, but that's a good story. So anyway, so in this network, you can actually check in terms of sensitivity which houses are least sensitive to problems with voltage and which ones are the most sensitive. So does anybody want to guess which house is most sensitive or most likely to have voltage problems in this network? C? Okay. So it turns out it's this one, and that's because it's the one that is the farthest from the transformer in terms of distance. So that current has to travel a long, long way, and you're dropping voltage the whole way. And it's on the most highly loaded phase. So you have all these A's here everywhere, so they're all on the same line. There's lots of current traveling through the line, lots of voltage dropping. So just out of curiosity, we thought, okay, we'll add an electric vehicle to this location. We'll see what that minimum voltage is. I forget what it was, maybe 225 or something. And now we'll take that vehicle off, and instead we'll start adding vehicles to the most stable ones, one at a time. And we'll see how many we can add in the good locations to the network to achieve the same effect as having only one vehicle in a bad location. So we started adding vehicles, and we added one more, and we added one more, and we added one more, and we added one more. And it turned out that at all these green locations, you can add electric vehicles to 45 houses, and you have the same minimum voltage in your network as adding only one at that red triangle there. And that was surprising, and we thought it was wrong, and we double-checked, and we thought about it. But actually, it does make sense. So if you add 46 vehicles, you'd have other problems. You might have too much demand on the transformer. But looking just purely at voltage, it does kind of make sense, because what happens is as you add vehicles to the less loaded phases, you're rebalancing the network. So in this case, C is very, very underloaded. So if you start adding vehicles to phase C, you're actually rebalancing the network. So that means you have less current running through the neutral, and that current through the neutral is like, with the impedance in the neutral, you're getting less voltage drop there. So very interesting that you can add 45 and have the same effect as adding only one. And that introduces some other interesting issues like fairness of charging. So should everybody have the same right to charge their electric vehicle? But you could have two people living next to each other, and if person A charges their vehicle and has a 80% chance of causing the transformer to fail, but person B next door was actually going to restabilize the network, should they really have the same right to charge? So,
change that electric vehicle to air conditioning and see what sort of response you get from the same person.
Yeah, well, absolutely. I mean, fairness, it's you think everybody should have the same right to charge. Like, it seems reasonable, but 45 versus 1. So maybe the easiest solution is to actually rebalance these networks and to have a really good idea of who's got the electric vehicles, who's going to be charging, make sure that the houses that have electric vehicles are on balanced phases. But that means being quite proactive as a network operator and understanding these things. So then there was another interesting thing that just sort of drove home some of these points, is that when we started looking at daily travel profiles, each horizontal line here represents one person's 24-hour travel profile. And these are real, these are based on real travel surveys. So if we take, for example, this one here, here's somebody who was at, so green and orange means that they're at home, white means they're away. So here's somebody left at 8:15, was away all day, came home at 7:30 p.m., and then was home for the rest of the night. And if we take the distances that were associated with these travel profiles, and we roughly guess at how long that would take to recharge if that were an electric vehicle, that gives you these orange bars. So this person here traveled quite a long distance, so they would have had to recharge for quite a long time. This person only traveled a short distance, they only needed to recharge for 15 minutes to reach full state of charge. But if you kind of plot this, you get a very nice visual intuition of some patterns. And the first is that all these orange sections where EVs would be charging if you plugged in as soon as you got home, they kind of line up quite a bit. So a lot of those EVs would be charging at the same time. But we have this huge amount of flexibility overnight. So whether your car charges at 9 p.m. or whether it charges at 1 a.m., as long as it's charged when you're ready to go in the morning, it doesn't matter. And there's this huge amount of space in the network where you can shift that charging to. So shifting charging, load shifting, smart charging is a well-known idea and very well studied. And actually, it is very feasible and has been demonstrated. So we had this Victoria electric vehicle trial, which I think finished about a year ago, but went for 3 years. And one of the phases in that trial was to demonstrate that this can be done. So the utility operator, in this case United Energy, teamed up with Dias, who built these charge points. And basically, I think they had 7 or 8 participants involved in this trial, installed all the stuff in their homes where the United Energy could send a signal. That signal got sent to the smart meter. The smart meter via Zigbee communicated with this charge point, and then the charge point either interrupted or reduced by 50% the amount of power that went to the electric vehicle. So for example, if you're running a network and you know you're going to have a lot of demand, or you've had a fault somewhere, or you've got problems, you could send a signal and it would instantly either interrupt or reduce by 50% all of your electric vehicles. And this is real, it was installed, it worked. There were a few teething issues at the start in terms of response times and so on, but they got it running in just a couple of months. So it's a very realistic proposition where we have smart meters anyway to centrally control all this electric vehicle charging. So so the next 3 slides I'm going to get just a little more technical and just explain how you can set that up as an optimization problem. So if you have a neighborhood and you've got a number of cars that come and go in this neighborhood, and you know what your typical demand is like, and you want to find the best possible way to charge those vehicles so that you don't cause any problems in the grid, so that they charge as quickly as possible. You can set this up as a standard optimization problem, which basically means you convert the problem to a standard format, which is well understood, and there are lots of standard solutions to find the best possible solution for it. So one of the things for the power engineers and optimization people in the room that we did have to do was we had to linearize the system. We had to assume that at the distribution level everything was mainly resistive, and that just helped us to turn it from a massively nonlinear, really complicated problem format into a nice linear program. So that was a shortcut we took. That provided us with the solution, and then when we had the solution, we implemented it and we tested it again in a fully complex load flow. And so what you're solving for is you're trying to figure out all the charge rates for all of your vehicles. But you don't want to do it only now, you also want to do it for 5 minutes from now, 10 minutes from now, 1 hour from now, because you're expecting things to change a little bit. And you might know that there's a lot of time available, or a lot of capacity available for charging 2 hours from now, but it's not available yet. So you're looking over a future horizon, you're solving for all the charge rates for all the vehicles, you implement the solution for your current time step, and then you shift that forwards, and then you keep doing that. So you're always recalculating, and you're always taking into account changes that might have occurred, new vehicles that might have arrived, other vehicles that might have departed, demand that might have shot up unexpectedly, and so on. And then I'm not going to go through each equation, but just there were equations involved. And basically the constraints, so the things that we're trying to make sure are not violated are excessive load at the transformer, too much load on any of the lines, too much unbalance in the phases, minimum voltage dropping below a certain level, and of course making sure that all the cars get charged on time. And then with the battery, naturally we had maximum minimum state of charge, maximum charge rate. So if you solve this, you have this nice way of presenting the problem. You can solve it. This is what happens. So these ones I've shown earlier, if you don't control it, you have this really high peak. You have voltage dropping below what you want. But on the other hand, if this is your state of charge of your car, it'll be charging at its maximum rate and it'll be charged as quickly as possible. If you control it, this is what happens. So you don't exceed that peak. You stay right within the bounds you want to. Your voltages stay right within the bounds you want to, but it means your car might not be charging, then charge for a bit, then not be charging, then charge, then not charge, then charge. But you're still fully charged by 11:30 p.m. So it might be that if suddenly you decide to leave at 8 p.m., you don't have quite as much state of charge in your car as you would have when you fully charge it. But on the other hand, you can plug it in and you can be sure that the grid will be fine and that you won't end up bearing the cost of huge upgrades to your network. So this was, in this case, what we were trying to do was we were trying to allow as many vehicles to charge as quickly as possible. But you can look at the whole problem from another perspective as well. So if you're an owner of, so if you're an aggregator, for example, you're trying to supply energy, buying energy at wholesale prices, guaranteeing people you'll charge their vehicles, but doing it for them, you might want to charge them as cheaply as possible. So if instead you try to solve this problem in terms of, I want all the vehicles to charge, but I want to pay as little as possible for the electricity, I'm only paying real-time prices, which go up and down quite a bit, then the solution looks a little bit different. So the wholesale price of electricity can fluctuate quite a bit, as you see in this top graph. That's actually a reasonably steady day. On some days, when you have a lot of stuff going on, it can shoot up to thousands of dollars instead of 40 or 50. So you don't really want to be buying electricity at that point. So again, you can use this problem, the way it's formulated, you can use this problem, you can just say, okay, solve for this instead. And then what happens is that all that electric vehicle load, this dark blue, gets scheduled for a time when your price is low. And so you're charging all the vehicles, still within the time that people expected, but saving a lot of money by doing it. So every network is different, and different networks will have different problems. Some might have a small transformer that's quick to be overloaded. Some might have long distances, which means low voltage is more likely to be a problem. So there's no sort of blanket statement you can make about every network. But we've analyzed quite a few. We've done analyses over different times of the year, different networks, different typical uptake profiles. And in general, what we found was that if you add vehicles to these networks and you don't control the charging at all, so people just plug in as soon as they get home, then after about 10 to 15%, you start to have problems. So if every 10th house in the neighborhood starts to buy an electric vehicle, then you might have problems in terms of low voltage or total demand of the transformer and so on. And that sort of range, 10 to 15%, is consistent also with studies we've seen in Ireland and in Portugal, where the networks are kind of roughly the same as here. So it would be a bit different in the US and in Canada. The networks look quite different. They have smaller transformers with a small number of houses connected, and they have different problems there. But for our kinds of networks and the networks in Europe, 10 to 15% is kind of where you start to see problems. If you control that electric vehicle charging and you schedule it to times when you have capacity, you can add a huge number of vehicles to the network. 80%, and 4 out of 5 houses having electric vehicles. And honestly, in the network I looked at, it was 100%. Like every house could have an electric vehicle, and because there's so much capacity overnight to charge them, you'll be okay. As long as you do it really cleverly and you don't charge them all at once, you can sustain a high electric vehicle penetration. And if you just think about what that means in terms of our networks, If you wanted to upgrade a network because suddenly problems arose from people owning EVs, you need to either upgrade the transformer or put new lines in or add some kind of voltage regulation or split it into two networks. Whatever you do, you'll probably be paying $100 to $150, if not $200,000 for a neighborhood of about 100 houses. So if we can cleverly schedule electric vehicle charging, we're saving about $1,000 to $2,000 per household. Really very rough analysis, and it depends a lot on where you are and what's going on, but just it's quite a bit, and it's something to think about. Another result that came out of this, if you schedule charging to times when the electricity price is low, you also have significant savings. So if an aggregator came in, like Better Place originally wanted to be, now maybe PowerShop, I don't know, somebody coming in who wants to control this centrally, being careful about when you charge them, you can save a lot. You can save 10 to 20%. So that kind of brings to an end one big piece of work, and I want to add a few other bits of research that our group did as well that are very closely related. The first is that one of our PhD students, Lou, has done a really nice piece of work on distributed demand control. So what I just talked about was centrally controlling all this. The network operator gets all the information in one location, makes a decision, finds a solution, and then tells every car what rate to charge at. But could you do it in a different way? Could you, for example, just send out a price signal? If you see your network's overloaded, just send something out. Reduce the amount of communication required, which in itself can be problematic. So there are a lot of methods that look at just sending out a signal and hoping everybody reacts to it, rather than two-way communication. But why not go one step further and say, can we do this kind of load control, this kind of demand response, entirely purely distributed? So can we make decisions at each point locally, so at your charge station, in such a way that you're reducing your negative impact on the grid without needing to have any communication with your neighbors or the network operator or anybody? And this is partly inspired by a device that IBM India actually developed called the N-Plug. So in India they have a lot of power outages. There are huge rewards for managing things carefully so that the network doesn't go down. And what this plug does is it measures your voltage over time, and if your voltage drops compared to what you're used to, then you would expect that there's quite a lot happening on the network. There's a lot of load, so it's not a good time to schedule something. But if your voltage rises, and you can measure this at home, you probably measure different voltage in your house at 7 p.m. versus 4 a.m. if you can get up to measure it at 4 a.m. So if you find that your voltage has gone quite high, that's probably a good time to schedule things. So they've actually developed this plug, which works really nicely, and there's no reason you couldn't apply that to electric vehicles. Just to drive that point home, if you look here at this graph, the dark blue line is the total demand in a network, and the dotted green line is the voltage at one of the houses in that network. So if you're at that house and you measure that dotted green line, you can see when that voltage drops really low, that's a bad time to start charging your car because there's huge demand on the network. But when that voltage is higher, then that's a good time. And so basically the method is very simple. You measure your voltage, you keep track of it a little bit, and then you can incrementally increase or decrease your charge rate in response to what you're reading. And this is actually quite similar to a lot of things people do in communications. In terms of when you download a big file, you'll see that it speeds up the download and then it slows down. It's the same sort of idea. And comparing this nice distributed way of solving things to the earlier perfect centralized way of solving things, it's actually amazing how well these distributed methods perform. So if you compare, again, the total demand, the local voltage, and the charge profile, you'll see that those constraints in the network are well respected. The charge profile is maybe not as good as you'd want it. Your car will charge slower than you want it to. In this case, not fully charged by 8 a.m. But definitely, I think it's a really promising area to work in and to develop methods for, because it's so much easier to implement. And you don't need smart meters, you don't need anything. You just stick the right plug in the wall and hope people don't tinker with it and start cheating. So. On that note, actually, a big question that always comes up with electric vehicle charging is how do you get people to agree to this load control? Everybody basically wants their cars charged as quickly as possible, and why would anybody agree, even if you're really proactive, which is network management, and a good citizen, why would you agree to have your vehicle charged at 4 a.m. instead of as soon as you get home? I think the things that are going to make that valid or useful or realistic for most people is a very careful way of designing the plans that you sign up to. So if you want to charge right away, then you have to pay a little bit more. If you're willing to delay it, then maybe you get on a nicer plan that allows you to pay a little bit less. So that's a really interesting area of study in itself. How do you get people to respond? Very interesting and very important as well. So we started to think about it just a little bit. What happens if you had 3 user plans, for example, and you wanted to, again, find the best way to charge vehicles while respecting that some people are willing to pay 3 times as much, and others twice as much, and the third don't really want to pay that much more. And so we tried to solve it, and we spent weeks on this, and the results just didn't make sense, and we couldn't figure out what's going wrong here. What is the problem? This algorithm keeps on assigning lots of power to the guy who doesn't want to pay for it and doesn't really care. Why does it keep giving this guy more power, even though it's not that important to? Why? Is there something wrong with the method? The method, check the code, everything works. And so there's, again, for the same reason as I explained before, these really strange things happen. So if we focus, again, this is a real network, and if we focus just on these 3 houses as an example, if we give all the houses in this network an equivalent load, then we have these kinds of voltages at houses 28, 29, and 30. 228, 238, and 217. So house 30 is on the most highly loaded phase, so it has the lowest voltage. And this is just a demo. We actually put huge loads on this network, and just to kind of emphasize the point. So you probably wouldn't see voltages this low at your house, hopefully. But now, just for the demonstration, what happens? So we leave everything as it is, and now we add an electric vehicle only at house 30. So the voltage drops a little bit. Voltage drops a lot here, and then it rises just a little bit on house 29. So you get this funny thing happening where you get a slight neutral point shift in the network. So we thought, okay, what happens if you take the vehicle away from 30 and you instead add one to 28? 28 is the least loaded phase. And so if you add one to 28, the voltage drops there, but the voltage doesn't drop much. In fact, it rises a little bit on phase 30. And we thought, okay, so it's neutral point shift, but also, again, you're rebalancing the network, which means you're getting less current through the neutral, so your total voltage is better. We thought, okay, what happens if we add vehicles at 28 and 30, and then we get these voltages? And the whole point of this example is if you look only at house 30, when you add an electric vehicle, the voltage drops too low. When you take that away and you add one somewhere else, the voltage is fine. And if you add 2 electric vehicles, it's still fine. And so basically what it means is house 30 can only charge their electric vehicle if house 28 is also charging their electric vehicle. So when we were trying to figure out how can we find the best way to respect people's plans, house number 30 might be willing to pay $1 million to charge their vehicle, but they can only kick on if house number 30 or the house number 28, who doesn't care, also kicks on. So suddenly there's these strange things happening when you try to bring user plans and fairness into it. So anyway, it's just it's a little quirky thing that can happen at the low voltage level. These weird effects tend to disappear if you have nicely balanced networks. So I wouldn't see them as a huge problem, but it's something to be aware of. So yeah, so that was the electric vehicle side of things. Now I'm going to switch gears a little bit and talk about some other work we've done on energy storage. So earlier this year, I joined IBM Research. I left the University of Melbourne and I joined IBM Research, and we have a small but very hardworking and very dedicated team working on energy-related topics. And one of the things, in fact, I should point out that Valentin and Khalid are actually PhD students here at the university, but they're interns with us at IBM. And Val, who's in the crowd, should get extra mention because much of the work that I'm about to present was his genius. So one thing we were looking at was with energy storage coming in, everybody's talking about energy storage. When will it be worth it for people to install batteries here in Australia? What factors affect it? So what are the sort of payback times and so on? So Australia is actually a really attractive market for energy storage because we have really high electricity prices. We had these really nice feed-in tariffs, which maybe some of you are on, but many of them are about to expire. So in the next year or two, a lot of us, I'm one of them as well, who got a nice feed-in tariff for solar PV, aren't going to have that anymore. So suddenly, the energy that our solar panels are generating isn't going to be getting us 30 cents anymore, but it'll be getting us, I think it's 6.5 this year, something like that. 6.8. Okay. So at the same time, we've got these trends in energy storage. So this is a nice meta-analysis of all these reports that have come out recently in terms of how the cost of lithium-ion energy storage is going to fall. And generally, all the major consultancies and banks agree roughly that they'll have by about 2020 and have again by about 2030. So with all these things happening, when will it be worth it for us to install batteries?
So how, sorry, just back on that, how does that adjust as of last week?
Do you mean with Tesla's announcement? Yeah, well, I'll definitely speak about Tesla as my last slide. So very timely. There was a big announcement on Friday. So what kind of, in figuring out how much value you get out of storage, you've got to, you start to look at, well, you need to know what's happening hour to hour in a day. So here you have a typical, a very average demand profile, the red line up there, which shows again your peak at around 6 p.m. So that's I think a August winter profile here in Melbourne. Obviously, your actual demand will jump up and down quite a bit depending on what you're turning on, so that's just a very average profile. Then this is, the green is a typical curve for how much your solar panels will be generating over 24 hours. So if you're paying, say, 30 cents for your electricity, but you're only getting paid 6.8 cents for how much of that energy you're feeding back to the grid, well then really what you want to do is store all that energy that you're generating, charge your battery, and then use it to offset your peak demand later on. So that's a very, very obvious reason to put energy storage in. And this is an optimal battery profile. I'll get to this part in a second, but basically you want to be charging while you have more generation than demand, and then discharging when you have more demand than generation. But there's another way that you get great value out of your energy storage, and that's playing that peak off-peak game. So many of us will be on two-part tariffs where you pay a certain amount overnight and another amount during the day, typically from 7 a.m. until 11 p.m. And if you can charge your battery when electricity is cheap and then discharge when electricity is expensive, then you're getting more value there. So those are two ways that you get value out of the battery. And actually, these are very nice, perfectly smooth curves. Actually, across a day, that could be going up and down quite a lot. You might be cycling your battery multiple times a day, depending on how much your generation is exceeding your demand at different times of the day. And one thing to keep in mind is that this profile will look quite different depending on what your parameters are. So in this case, you're getting way more value out of self-using your PV generation than you are out of playing that off-peak to peak game. So when you're charging during off-peak time, you only want to charge a little bit. You don't want to fill your battery, because if you do that, you don't have enough time to discharge it so that it's empty when your solar panels are generating. So it's quite important. It's the same sort of thing. It's quite important to be able to look ahead in time and know what to expect so that you get the most value out of the battery. You don't want to fully charge it overnight because you're expecting a lot of sunshine. So wait, let me put that in a different way. If you're expecting a very sunny day, then you want to make sure your battery is empty at the start so that you're getting the most out of that solar generation. But if you're expecting a very cloudy day, then you want to fully charge your battery overnight so that you can discharge and offset your household or your daily demand. So it brings into play forecasting, and I actually don't know what some of the products you were talking about, Peter, last month, how these inverters or how some of these storage systems do it. I don't know how Tesla decided to do it, but if you really want to get the most out of your battery, you do need to have some sort of forecasting. You need to sort of know what to expect. And I don't think many of them do much of that at the moment. Just a quick note on how we actually solve this. In this case, we solve it as a dynamic program. I'll just be very brief on this one. But basically, you look at all the possible states of charge that your battery could be in right now, or 5 minutes from now, 10 minutes from now, an hour from now, and you pass forward and you say, okay, I could charge, I could discharge. How much value will I be getting going from any of my states of charge now to 5 minutes from now, 10 minutes, and so on? And then when you find the best value at the end of it, you work your way back and you figure out how you got there. And that tells you how you should have charged and discharged. So we applied this method. We did this analysis where we took demand data from 100 houses across Melbourne. Each house will have slightly different profiles depending on whether it's retired people who are home quite a bit, or typical workers who are commuting and who are away for most of the day, or mothers at home with kids, or so on. So we compared 100 different demand profiles, took a typical PV generation profile, then came to the point of figuring out how, if we look at this over 20 years, what's the battery going to be doing? Because batteries' capacities degrade over their lifetimes. So it's quite hard to find information on this, and all these technologies are so new that people haven't really had a chance yet to do long-term analyses of aging and so on. But we did the best we could with what we had available, and we assumed that with a 5 kilowatt hour battery, you avoid the top and bottom ends of that state of charge where it ages really quickly, and within that the middle band, you basically have 4 kilowatt hours to use, and over time that will, with the number of cycles you use, degrade. So at the end of its lifetime, you have much less to use. We ran this analysis, we compared these 100 houses. One thing we found that was quite interesting was that roughly 78% of the energy generated by these solar panels, given these demand profiles, would be fed back into the grid. So about 78% is typically fed back. So there's huge potential there for, instead of feeding that back into the grid, storing it and using it later. And prediction is difficult, especially about the future, as used. So, but depending on what assumptions you make, in terms of how energy storage costs are trending and how our electricity prices are likely to rise, you can look at these different scenarios. And so if we look at what's happening with lithium-ion battery prices, by about 2020, with a sorry, just confused for a second. Okay, so for an average expectation of how battery costs are going to change over time, you're looking at a payback, an average payback of somewhere between 5 to 10 years. Another really interesting result that came out of all this was that even though people have very different usage profiles, the results were pretty much the same for many houses, many different profiles, many different people. So when it becomes worth it, when you get these, when you excuse me, when you have the right sort of trends, when you get the right sort of battery price, and if you assume a certain rise in electricity prices, it will be worth it for people at almost exactly the same time. So just like with solar, where you got a lot of people very quickly jumping on the bandwagon and installing these things, with storage, you can expect the same thing, regardless of what kind of profile you have and where you live. So it's a very realistic possibility that within 5 to 8 years, people are going to buy these storage units and install them like crazy. And so we were talking about, we had a really nice discussion about this a month ago. This is going to lead to huge changes in the way we manage our electricity networks. Some real problems in terms of if everybody starts to go off grid, who starts to pay for the electricity grid, and so on. And very timely, just 3 days ago, there was a huge announcement that we were all awaiting with great expectation. Tesla, the electric vehicle manufacturer, has announced home energy storage as well. So they, for anybody who doesn't know, have committed to building a gigafactory, I think $5 billion gigafactory that's supposed to pump out, 50 gigawatt hours of storage per year from 2020 onwards. So huge amount of energy storage being produced. And it was only natural, it was only to be expected that they're not looking just at electric vehicles, they're actually producing these units for home use as well. And so for $3,000, you can get yourself a 7 kilowatt hour battery. 7 kilowatt hours for most of us will pretty close allow us to go off grid. That doesn't include the inverter, and it doesn't include the installation costs, which may actually double the cost. But nevertheless, it's a big improvement on all the prices I've seen for storage and so on. So pretty exciting. And yeah, so I was at the EV Expo a week ago. That's my son Sebastian. He is totally not convinced, and he's very skeptical. But if any of you are skeptical about anything I've said, then I'd love to answer your questions. So thank you very much.
Okay, ladies and gentlemen, thank you very much, Julian. Questions, please.
I think that was fascinating. Back in your electric vehicle section, we had the graph of the horizontal bars of white, green and orange. Was any consideration given, or can you give any thoughts on what would happen if during that window of lots of overlapping coincident charging, you instead actually had a fourth colour which was discharging, where you were feeding back into the network and willing to sell it back?
Well, absolutely. So the discharging would probably happen actually where they're all charging, because that's the peak time, right? So you want to be discharging at that peak to alleviate the load. So vehicle to grid, vehicle to home is an awesome idea. It makes a lot of sense. We never looked into it so far, just because whenever we talk to people in the industry and to car makers, these batteries come with warranties. So they'll have an 8-year warranty, 10-year warranty, whatever. And if you start to discharge to the grid, then you're doubling the number of cycles it goes through. And all of a sudden,
Or deepening a cycle.
Or deepening the cycle. So the car makers suddenly then have real trouble predicting what's going to happen to these batteries, and they can't provide these warranties anymore because the more they have to have them. So it's brilliant. I know in Japan they're doing a fair bit. I know that they're really concerned about dealing with power outages and so on. And they
This 1 or 2 kilowatt hours from the battery back to the grid would be enough.
Yeah, absolutely. I think it's a brilliant idea. So it's more a question of getting all the different players involved to agree on these things with each other, which is difficult.
Do you see the spot price retailers like PowerShop helping move this curve?
Which curve? The curve of energy storage, or
Yeah,
the
man, curve. What?
At the EV Expo, I saw PowerShop had a branded Tesla on display, and they are also in partnership with an electric scooter company to reduce the electricity cost of charging electric scooters. So they're pushing all this like crazy. One conundrum that I had throughout the 3 years working on this project is we have this decreasing demand in Victoria. It's a huge problem for network operators, retailers, a lot of big players. And why didn't they just decide, why don't we just push electric vehicles like crazy? Why doesn't SP AusNet tell me, Julian?
As stupid as ever.
No one.
But why don't they offer free charge points if you buy an electric vehicle or something like this? Because suddenly you get huge electricity demand. It reinforces all their business plans. It would just work for so many players in the grid. So PowerShop, I think, are going on that route.
Just interested in your last slide about 7 kilowatt hours might be enough to go off grid. The average daily consumption in Victoria is about 14 kilowatt hours,
Yep.
and obviously in winter you have some very cloudy days. So could you comment on that?
Yeah, well, I guess it depends very much on how much the household uses. But I'm assuming if you're a house with PV panels, that you've got some generation throughout the day, even on cloudy days. 7 kilowatt hours. I can't remember what we found in our study, but generally you need less storage than you think, because you can. You're not going to be, during the day when you've got excess generation, you're charging it. At night, even though you may be using 14 kilowatt hours a day, a big chunk of that may be offset by your PV system already, and you don't actually use that much overnight when your battery would be running. So it depends on the house. Not every house could work on 7 kilowatt hours, but I think a lot could.
Is it stackable as well? It usually be stackable, right?
Yeah.
By 2.
Sure, yeah. If you got $6,000, that's not
So you mentioned that different parts of the grid become most destabilised. If you put power in, is there a point that you can introduce battery power into the grid to offset that destabilisation? Is it the most sensitive house, or is there a point that you can introduce power from a battery to grid control?
Absolutely. So you would want to introduce power, if your phases are unloaded, you'd want to introduce it on the most heavily loaded phase. Sorry? Yeah, because that's where you're offsetting things. We are introducing power already with PV systems that are throughout these networks. So we looked only at EVs, which are loads, which are drawing energy. But all these things also happen in reverse when PV systems are supplying energy. And so one problem that we've had in Victoria is that your transformer is set at a certain voltage. That voltage then drops as you go down. They can pick that voltage, they can leave a little extra space by going up or go a little further down in terms of where they tap that. But actually, they haven't been tapping them up to increase voltage. They've, in many cases, been tapping them down because so many people have installed PV panels that a problem that they've seen much more in networks so far has been high voltage when all the PV systems are generating. So it's actually quite difficult for network operators to deal with this voltage going up in the middle of the day when you're not charging EVs, but all your panels are generating, and then voltage going really far down around 6, 7 p.m. when all the EVs come home or whatever else you're using, and there's no more PV being generated. So it's a real problem. But
Thank you, Mania.
Yeah, so just a small comment on another study that was done in terms of increasing the utilization of wind power.
Yeah.
For example, if all electric vehicles weren't charged for batteries, doesn't matter, to 100%, but to 95%, they could absorb what would otherwise be wasted wind energy.
Yeah.
So in fact, what they do, they lower the cost per kilowatt hour by increasing the utilization of the grid.
Yeah.
So instead of feathering the blades, we actually use that information. But another question, when you looked at those sort of demand response mechanisms, of what would get people to respond, have you looked at transactive control? Because to me that seems, and it is an IBM model. It's one that we think is just brilliant. If you bring it like literally to the edge of the grid, even between your PV and your battery, if they negotiate, so the battery says charge me, and he says no, the grid is paying me higher, that sort of thing. Yeah. Have you looked at that yet? Because
absolutely, And transactive energy is we hear it a lot at IBM. It's a priority. So. Yeah, it's a work in progress, and it's not a straightforward thing to do. How do you value a kilowatt hour one way or another with all the different players involved? Absolutely, I totally agree.
Not local.
Yeah. So the players, I mean, like small, like the PV panels, the inverter, the local grid, the neighbor, all that kind of thing. I don't mean the big energy players.
Yeah, I've got a Bolt. And it's an electric car, and I have a price signal that tells me when I charge, and the car also permits me to say when the off-peak rates are. So when I charge and allow the car to determine that, it charges at 11 o'clock. It costs me $1.50 to do a full charge.
Yeah.
If I do it other times, it costs me $4.
Yeah, that's great.
So are you using this piece to work at changing the market structure by changing the regulators that set peak and off-peak times? Or
so tariffs are a huge part of all this, and how to structure tariffs and how to introduce pricing. Because there's a problem with that too. If your prices spike at one point in time, everybody puts the timer in their charger on, start charging at 11 p.m. And that's true with pool pumps as well. And I think you can even look at statewide demand, and you'll see the peak, the regular peak, then it goes down, and then it jumps up. It jumps up just this little bit at 11 p.m., and that's because everybody's pool pumps are going on at 11 p.m. because the prices are low. And that's really difficult for network operators to deal with as well, because from one minute to the next, you've got to ramp up all this production. So that is definitely an important challenge as well, that you manage these ramp rates and these sudden spikes. So the way that we've solved this optimal energy charge takes care of that, because all the problems in the grid are modeled as constraints, so it solves that. But in terms of actually getting people to do this, it would have to be more than just a 1 hour, one rate, another hour, another rate. It would have to be a sign up for this plan, and we'll charge it at 50%, or we'll charge it at $1.50. Sign up to this plan, we'll charge it right away, but it will cost you $4. So yeah, it's an important thing.
Right at the back then.
I'm very fascinated with that particular diagram you have there, and that the networks haven't seriously considered the simple process in solving that problem. Keeping that in mind, I'm suggesting there's a more difficult problem they could deal with. If it's worthwhile us considering using a battery to help the grid solve its balancing so that we get a benefit, do you think there's any possibility that the grid will develop the intelligence to take some of those steps within its own network? Because if I can buy a battery, so can they.
Oh, you mean are they putting in batteries for grid level
I'm not
energy?
saying are they.
Yeah.
I'm just saying if I've got an incentive to do it,
Yeah.
how come they're not responding to the incentive to do it? And they have many different other technologies. We're talking about small-scale batteries on a domestic level, but there's hydropower repumps and all sorts of other mechanisms that they have.
Yeah.
Why are they not responding and dealing with those issues? Do they want us to fix it for them?
Well, they are slowly. Just last week, we had a chance to visit SB Osnet's massive battery that they have up in Thomastown, a 1 megawatt hour system, which is very impressive. At the moment, it's a cost issue as well. For a lot of them, energy storage is still expensive. It's actually more expensive to put in a diesel generator, or other things. Maybe you're alluding to the fact that the frameworks aren't right and that the system isn't properly set up, and I would totally agree. So things do need to change. Network operators do need to become a lot more responsible for the efficiency of their networks, rather than the gold plating that we talked about last month as well, which doesn't make sense.
Can I have a quick follow on to that one? Just to follow on to that, is part of the problem that is behind the transformer? So Rob's idea is really working at the network level, but not down behind the transformer where you need it?
The operators, as in they don't... Yeah, so they've completely neglected this part of the network forever.
But the fixes Robert was just talking about are at too high a level to get behind the transformer.
Well, you have problems at both levels. I mean, you need to fix things within the distribution network where you have certain local problems, but you also need to fix things at the substation level and at the transmission level. So there are different types of problems that you get at different levels, most of which storage can fix. At the distribution level, they're really, my impression is they are really just now starting to get a real feeling for what's really going on. And like I was saying, they haven't needed to know exactly what's going on. It didn't matter, but now it does. So they're working on it, and hopefully they'll work on it quickly, because I mean, when you think about it, unbalanced networks, all this additional current going through the neutral needs to come from somewhere. It needs to be generated. Huge losses and huge amount of waste, and all you have to do is rebalance. All you have to do is send someone in, this house over here, reconnect a bit, and your network's so much more efficient. And the incentives for how network operators are evaluated and so on haven't been there. They haven't needed to. They didn't need to prove it. If anything, they want them to be inefficient because then they can install more new stuff. So I'm not saying that's what actually happens, but it has been a problem.
I was going to ask a question, but I think you may have already answered it. Is the network operators been doing the right thing by us consumers by not adjusting their things up and down, their voltage regulators? They just made it too hard for people to go solar like they've done with everything else. Some sort of inquiry. They're the first ones to say it's going to change the curtain colours, don't do it, guys.
Yeah, so with SB Osnet, because I'm with SB Osnet, I know that beyond a certain amount of capacity, your PV system, you had to get special permission, I think about 4.5 kilowatts. Also, I've heard
of other people being told they can't have as many panels as they want because it's going to upset the... I've even heard of people who are maybe the fifth ones on the network to want to install solar panels, and they weren't allowed to because it is... I don't want to stand here defending network operators, but there are real challenges involved in allowing all these things to enter our distribution networks. So when you have sets of solar PV arrays all in the same phase or in the same network, and they're all generating, then your voltage can shoot up, and you can even get power flow going back the other way, which nothing was ever designed to do.
So there are difficulties, and it's been a real headache for network operators. But at the same time, it makes so much sense to, they do need to innovate, they do need to integrate all this stuff. I do agree.
There must be some weather forecasting happening at the generators level, because when South Australia produces lots of wind power, like they did, I think it was in November last year, like huge amounts, we buy it very cheaply for Victoria, and they still charge us the same amount. So that's when they make huge profits.
Yeah.
So I would suspect that they have good weather forecasters to work these, the mathematics out on that.
Yeah.
So why can't they do it in the other parts of the business, like what you've suggested there?
You mean forecasting the demands or the generation or
any other generation, any other area of activity that they're involved in? They don't seem to be paying as much attention as they would be in terms of generating revenue if the wind is blowing in South Australia.
Well, they're paying more attention to what makes them money than to. So it's unfortunate. That's just that's where the incentives are.
With generators or distributors, they're two different parties.
Yeah.
Eating incentives.
Yeah.
I wanted to ask you, the study was only based on residential areas, rather on the household load profiles.
Yeah.
Is there also a study done that includes commercial areas or industrial areas, because that could kind of fit the load profiles, right? Because if you charge at your office or the office power, like the load profile at the office would be controversial to the residential areas in a way. So that could kind of make the picture look a lot different.
Yeah, so it makes perfect sense. So if your workplace had charge points installed and you could charge at work, or while you're at a shopping center, or anything you're going to in the middle of the day, then the load of your EV charging is right in sync with the PV generation profile, and then it would make a lot of sense. So no, we didn't look at those kinds of networks. One of the motivations was that people typically prefer to charge at home. At least the early studies, they did, they've got some big EV trials in the US, and they put out all this charging infrastructure, shopping centers and movie theaters and so on, and most people just like to plug in at home. So, but I mean, that's the early adopters, and things might change with different incentives and different prices. If it's expensive to charge at home, you might say, oh, nice, for free at the movie theater, great. But no, we just look at residential.
Julian, as you know, the plug-in socket isn't just a regular mains plug. There's communications involved there. I'd like your thoughts on what issues there are on that plug-socket interface. Is it sufficient that the SAE J1772 socket is on most vehicles but not all? You talked about the EV trial and how there was signalling back that allowed throttling of that charging to take place. How does that happen? Any thoughts on that question?
Standards are super important. I believe the J1772, and you or maybe other people know more about it than me, but I believe you can provide a maximum charging power. So you can specify the maximum limit. And I believe that's how when they did the real trial, where they actually did central load control, that's what they basically provided. They provided no limit, or they said cut charging by 50%. Your question was, should chargers...
Are there issues with that interface? Is it sufficient, do you think, for the design of networks going forward? Are there things that it needs to do? Does it have enough capacity?
Yeah, I'm not a huge expert on what's happening with the standards. Certainly, to enable any of this to happen easily, you'd want interoperable standards. But for the rest,
Like the Tesla doesn't use the standard.
Yeah, they do their own thing.
But there is another aspect to that we argue with the regulator and failed. Basically, is the communication in the charging point in the car. Like Tesla comes with communication. So you talk to the car and it controls the charging. We argue that the meter should be in the car. It's called a roaming linear, and the networks objected it so hard, they said it's the end of the world as we know it, and decided that the meter is in the charging point, which allows for much less benefit There's reasons for that. So we failed on that argument. There's many issues there.
Okay, back here.
Yeah, I was just having a look at the graphs and two main sections of the presentation. The first one on electric vehicles and the second one on battery storage seem to be addressing the opposite problems. One of trying to fill load into off-peak nighttime area, and the other one trying to feed charge into the
I'm not sure that's totally you're right, but so you're right with the electric vehicle stuff. We were trying to schedule load whenever there was capacity in the network, whenever there was. With this, what you're saying is with this profile, the charge discharge, the state of charge, do you think we'd be doing the opposite? Is that what you mean?
I mean, with this one here, you're trying to save like accumulated generation during the day and put back into the network when the sun goes down.
Yep.
So in the future, when we're not dealing with hopefully this huge dominance of centralised generation, which I want steady load patterns, when you have this huge swell of generation through the daylight hours, you have the opposite sort of a problem of balancing.
Well, in this case, what you'd be doing, I hope I'm not misunderstanding, but in this case, what you'd be doing is your actual net impact on the grid is zero, because whatever you're using, whatever demand you have, your generation is offsetting, and then whatever extra generation you have, you're storing locally, so you're not feeding it back into the grid. And then you're only using that available energy when you need it. So if anything, your impact on the grid is much, much reduced by the storage. So I wouldn't see, unless you have problems of, if you have a lot of these in a network and everybody wants to charge at off-peak time, same as with the other question, pool pumps and things, there's a risk that all the batteries say, okay, we really want to charge now before we start hitting peak prices, and they all charge at the same time. And then you get a huge ramp up of demand on the grid, and that could be a real problem. So, is that what you have? Yeah?
I think one problem is grid leveling, and the other is matching generation and load price. The grid wants it to be level, but at the moment generation is designed to be level, but in the future it might be very irregular. The load generation might not be trying to just flatten out.
I think there's a general issue with the incentive that you have, right? I mean, on the one hand, you have the grid operator, where it's about how do we operate the grid in the best way possible so that everyone can charge. And on the other hand, you have the individual who says, well, I'm charging my batteries, and now suddenly I have to pay for electricity, so let's try and discharge. We need the incentives to be passed through a little bit better, so that everyone has the same incentives and everyone starts working together. And that's just not the case at the moment. And that's, I mean, it comes back to generators and distributors all having different incentives. Really, we should see the whole system and say, where do we want the system to go, and how can we share the incentives out so that every single player contributes to us all moving in the right direction. That's just not the case.
And very, very difficult.
With your two models, you showed one where you had centralized load control.
Yep.
And I'm just wondering, what are the steps required, given what we have now in the system? What are the steps required to get to that centralized load control? So it looks much better, right? The outcomes.
Oh yeah, okay. Well, we've all got smart meters in Victoria. So that's one area where Victoria is actually leading the world in a way. There's only a few places in the world where every single household has a smart meter. That helps. It's not, you can use that smart meter. The other thing you would need is charge points that speak to that smart meter, which brings standards into it again. It wouldn't actually be that difficult to do, in my opinion. I think for the actual network operators, you have even more data coming in, even more decisions you got to make. Scaling up, I think these kinds of solutions would work just fine. I don't think you'd have huge problems because you're solving them all locally. So
you already, if there are imbalances in the system, they already know about the smart meters? There's imbalances?
So the smart meters will feed back, I think different distributors have different amount of information they get from their smart meters. Some of them will get the voltage profile. And then when you see the voltage profile, I think it's pretty straightforward. It's not that difficult to compare all the voltage profiles in the network. Some of them will be going like this, and they might be higher or lower, but they've all got the same pattern. And other ones will be going like this, but they've all got the same pattern. So you can use that, and you can fairly easily, I think, figure out which houses are on which phase. Whether they're actually doing that yet, I think in trials, but maybe not yet on large scale.
No, somebody, yeah. Gentleman at the back there. Yourself there.
Yes. To take that last, reduce that proposition to absurdity, when I become the very last house in my street, which is still connected to the grid, how the hell am I going to afford it?
Sorry, I don't have a. We had a good discussion about that last time. It's a really difficult question. Sorry? Just leave. You have to go off grid. Everyone will have to go off grid. But what about people living in apartments, or what about people who can't afford to buy the initial install cost of solar plus storage?
Oh, it's very rough, is it?
So that street's not the street where I live, or any street where there's inner city terraces where people don't have on-site parking. So I'm just wondering, when people have to park on the street, because they're not very small blocks, what impact does it have on the network if somebody is installing charge points on the footpath, say?
It just depends a lot on what the local network is like. If they're installing something right on the footpath, it could be that it's right next to the transformer and has zero impact. Or if it's right at the end of a long line, it might draw that voltage down quite a bit. It just totally depends on what's happening locally.
I know the whole lot of grid topics being done there, but there's somebody who lives off grid. I can assure you that the pattern is not going to be that everybody's going to choose to go off grid. For exactly the point that was raised, like if you choose to go off grid, you've got to have your storage and your generation to meet the worst possible combination of days that might happen in 5 years. It's just not economic to do it. It'll only take a few people to try it and find out, oh shit, in 3 cloudy days it didn't work and I had no power. The grid is a really good system to be connected to, and once we get the incentives lined up, it'll be magic when your daily, you're matching your daily demand from your PV and using that from a small battery that's just optimized just for that one job. But staying connected to the grid for the 3-day issue in winter and the bigger, longer period swing makes perfect sense, both technically from an engineering point of view and economically. So I think this idea that everybody's going to go off the electricity grid and you're going to be the last one on the street, I don't think it's something we need to worry about, and I don't think it's something we should promote either.
Well, when you think about
if 95% of everyone's power is off the grid, the companies are going to go bust, and unless the government control, they're not going to be able to support the grid anyway. So at that point,
absolutely. But I think that the model, that it'll be in all of our best interest to find a way to make that work for the grid operators as well.
Yeah. When you think about it a little bit, the history of electricity generation and supply, we started as lots of little individual generators, people having small networks, maybe street lights in one city, maybe a little neighborhood here, a little neighborhood there. Over time, they realized there were huge advantages to tying all these things together because you get the diversity in the demand, so you don't get as many peaks. When you have a lot of customers, it's much smoother to know to predict what's happening. So over time, all these networks joined and became bigger and became bigger and bigger, and now we've got these huge interconnected grids because it's better. But now we're going the other way, and everyone's saying, well, no, it's actually so much better for us to divide this and have a microgrid here and not draw a line out to there. And so it's the things that the grid provides are very valuable in many situations. And to just say we should ignore the grids, I don't think that's the solution either. So I completely agree. But the incentives.
That too? Sorry, mate. I charge my EV at night. My usage went up from about 8 kilowatt hours to about 16 or 17 from the day I bought the car. But I also monitor my electricity usage with a real life monitor.
Yeah.
When I put my kettle on to make a cup of coffee, that spikes it. Absolutely. Anyone who thinks they're going to go off grid still haven't got a standard lifestyle, the way they have now, it just doesn't work. The gentleman talking about being off grid, you just got to watch everything. And that's just worrying about the day-to-day. When there's no sun for 3 days, that's another issue as well. So people won't go off grid once they see these little problems. Being connected to the grid, great, we'll still have the power.
3 minutes left, this gentleman here.
Isn't there a real problem? Your calculations where you can say you can buy a battery pack and given all the tariffs, you pay off in 10 years' time. Isn't there a real risk that lots of people buy battery packs, so all the tariffs will change and you won't be able to make the same money?
It's possible. Again, the main value you're getting out of it is self-consumption. So storing.
That's because you're allowed to self-consume and get not pay for it.
Yes. So what you're saying is, if the whole tariff structure changes and prices change such that that you get paid even less, or that your electricity prices are down, or
they sell it back to you to use what's coming off your grid.
it's entirely possible that the way they, or even that they bring in much larger network charges, things like that. It's totally possible that could change in a couple of years. Yes.
Just going back to the life of the grid after you introduce storage, it'd be interesting to see how the cost of maintaining that grid reduces as well, because a lot of the costs and the maintenance comes in because we're pushing the grid so hard. If you go and reduce the load of the grid, then the lifetime can go and extend it, and the costs come down. It'd be interesting to see how that's affected as well.
Okay, any other? Right.
I'm just interested in a few more details on the SPOnet storage. Is it solar charging or diesel? And is it, what's the purpose? Is it load shedding or?
It's maintaining, it's peak shaving, from what I understand. And it's, part of it is just a trial storage technology, and understand it better and so on. So they have mainly industrial neighborhood up there. They've got this huge battery. They also have a diesel generator next to it, just because they could only afford this size of battery, and to do proper peak shaving they needed a bit more, so diesel was cheaper, so they've got two megawatts that they can actually shave a peak with. And then when there's too much demand in this network, rather than having to go in and put in new cables and a new transformer and so on, instead they just switch on the battery, and for those few hours, or even every day, they make sure that the total demand stays below whatever they set as a set point. And then but they don't have any PV or any local generation, so then they just recharge off the grid at night.
Are you speaking at the energy storage conference next week? Or?
No, but I'll go there. I'm looking forward to it.
Okay. So we're going to ask Michael to give a little plug to that solar and energy storage conference. You know,
the May 13, 14.
Yeah.
Well, I suspect the whole audience already knows about it. Yeah, it's a combined solar conference and energy storage conference. The first formal year of the energy storage one. And solar's been going for many years. It's free at exhibition buildings, but strongly recommend you register online, because the queues can be horrendous registering there, but it's free, and lots of interesting talks, lots of interesting exhibits.
Okay, well, I think we're about out of time on the questions, so can I ask you to join me in thanking Julian? Now, the usual little plugs that I have to put in. Firstly, after this event, we're going down to the pub at the corner, so you're welcome to join down there and come and have a drink or a meal. I'd also like to bring to your attention the idea of the concept we have of being a baseload supporter. If you can donate $25 a month to be on zero emissions, it would help us enormously. If we can get 1,000 baseload supporters, we would have no funds problems at all. So if you would like to, please name and number at the desk there, or email, and join up and become a baseload supporter of BZE. Our next discussion group will be on Monday the 1st of June. BZE Research Director Gerard Drew will be presenting the new report, The Fossil Economy. This report investigates the revenue expectation of Australia's emissions-intensive exports, comparing Australian government projections with projections from the International Energy Agency. Should be fun. Very important, please note, this venue is not available during June and July, so we'll be in the physics building which is just a walking distance across Swanston Street from here. If you check the BZE website and your emails for the map and directions on how to get there, you'll find that will happen. You can catch up on YouTube recordings and download slides at the BZE website. Julian, has this got going on to BZE?
I believe so.
Thank you. Yeah. And if you like the storage topic, check out the latest BZE radio podcasts. We've got interviews with Tesla Motors, Tritium Australia, Tritium Australian-made EV charging, and also Sunverge solar storage and battery storage kit from California that's been used by electricity distributors over there. And finally, do go to the BZE website, http://bze.org.au on podcasts. Thank you, ladies and gentlemen. See you at the